Hi, I'm Tom Sutliff. I'm here today to talk about the Artemis lunar exploration program of our future by looking back at an aspect of our Apollo program of the past. Specifically, I'll be talking about a lesser known element of the Apollo astronauts' visits to the moon, dealing with the use of radioisotope power systems, or RPS, to help perform science on the moon. Now, in 1969, the NASA astronauts visited the lunar surface for the first time. Everybody knows that. About 5 more visits and 12 visiting astronauts later, there was a series of science investigations that were left behind. They were known as the Apollo Lunar Surface Experiment Packages. Apollo 12 through Apollo 17 left these packages behind. I'll come back to Apollo 11 in a couple of minutes. But 5 science packages were left behind, the ALSEPs. Their goals were to continue operation across 2 years for science. Of course, they needed to be remotely operated. Solar and battery power weren't options, as every lunar night was 14 Earth days long. So the use of radioisotope power became important, and each ALSEP had an RPS unit that provided electrical power for the long-lived sustained operation of the science package. So it's correct to say RPS provided the power to explore. Now, not only did RPS provide power for the lunar missions, but power for RPS has enabled 27 other missions in the United States since 1961. Some of the more compelling NASA missions included, from the top left clockwise, the Galileo mission to Jupiter, which, for example, found water below a thick ice layer on Europa. Pioneer, getting the first up-close glimpses at the deep ends of our solar system. Cassini, exploring the Saturn system, its rings, the plumes coming off the moon Enceladus, the lakes on Titan, the New Horizons spacecraft passing by Pluto and Charon and out deeper into the Kuiper Belt. Curiosity, and soon the Perseverance rovers exploring Mars in its roving across the surface looking for water. Ulysses on the sun, well, not on the sun, it was 5 AUs, 5 astronomical units from the sun, but exploring our nearest star. Viking, exploring Mars with a lander, basically a search for life system, and Carl Sagan, pictured in this Earth photo next to a Viking lander, was one of the driving forces behind this mission. Voyager on its grand tour of our solar system, and now flying into interstellar space. And finally, the ALSEPs in the middle, doing science experiments on the moon. The robotic systems that we provide a journey of exploration for us here on Earth. Missions first, generally like Voyager and Pioneer, didn't know what they were going to find, and they were really explorers of fly-by nature. Later missions such as Galileo and Cassini, they orbited a specific planetary body. Other systems like Viking and the ALSEPs were stationary surface systems. Curiosity, for example, has mobility, so it can rove across the surface and explore beyond a single landed site. As each of these RPS-enabled missions, such as the Apollo ALSEPs, sophistication grew. They wrote textbooks with what they learned from the science that was conducted. They've searched for water on Mars and been successful. They've found strange ocean worlds in a variety of places in the solar system. But questions still remain. Was there life? Is there life? Are we alone? So let me back up and talk about this thing called Radioisotope Power Systems, or RPS, so I don't stumble on it. RPS, simply put, is an energy conversion device. Your car's engine is an energy conversion device. It takes chemical energy from gasoline and creates mechanical energy with your motor to propel your car. An RPS is a thermal to electrical energy conversion system. The thermal energy produced by the natural decay of plutonium-238, an isotope. It decays, it emits heat. The upper right image shows a pellet of plutonium-238 prior to being encapsulated in a series of systems known as modules. These modules ultimately are placed inside an RPS. Once the heat source is installed, it heats one end of a series of solid-state static devices. These are known as thermoelectric couples. One of these tiny couples is shown in the engineer's hand on the lower left. When the other end of the couple is exposed to a cooler environment, usually via radiator fins, shown in the graphic upper left, the couples produce an electrical potential. Basically, it becomes a thermal battery. When wired up appropriately, this electrical energy is sufficient to operate instruments, devices, commercial equipment, communication equipment, to conduct science experiments, or operate an entire spacecraft. While the RPS animated here is a representation of the multi-mission radioisotope thermoelectric generator, that's the current system that we have available. The Apollo ALSEPs used an earlier generation system called the SNAP-27 generator. It looks quite similar to Curiosity, but there are fundamental differences between them. For mission-unique reasons, the SNAP-27 generators were deployed by the Apollo astronauts. They had to do the final assembly on the surface. The plutonium-238's encased in the lower left holder, and they actually fueled the systems on the surface of the moon. They also had to put the ALSEP science packages together and carry them across the surface and deploy them away from the lunar landers so they wouldn't be damaged when the crew took off again. We've talked about Apollo 12 through 17, but let me back up a minute and talk about Apollo 11. Even Apollo 11 used radioisotope power. They used the thermal portion of radioisotope power, not electrical. They used it on what was called the early Apollo science experiment packages that were solar powered. They were shorter duration systems, but the radioisotope heater that was included on it allowed the package to survive the 14 days of lunar night and then still allow operation using the solar panels the next lunar day. Well, let's back up and talk about the lunar night here for a minute. The concept of 14 days of darkness sometimes can be confusing. Remember, the same side of the moon always faces the Earth. This is the side the Apollo missions landed on. We look at the moon and it's bright in the night sky, and we call it a full moon. Then it might appear as a half moon or a crescent moon, and then a new moon one would not see from Earth, but the moon is still illuminated on the backside. That's not a dark side of the moon, but it's the back side of the moon. There is no dark side of the moon. Well, not continuously dark, unless you're in a permanently shadowed crater. That's another science talk, though. Anyway, each ALSEP site was continuously operated, whether it was in daylight or even through a long night, because of its radioisotope power source. Now, a little bit about science, a little bit about system, a little bit about engineering, because I'm an engineer after all. One of the most interesting instruments for me was the ALSEPs seismometers. The foil-covered instrument in the center of the picture is a seismometer. The instrument was emplaced on multiple landing sites to detect moonquakes, as the data on the right will show was happening. It was important always to be listening and operating because, while moonquakes don't happen on a predictable schedule like the old eruptions of Old Faithful. Anyway, I promised I was going to talk about the future, but the past is always interesting too. It does teach us lessons for use in the future. All the ALSEP stations were commanded off in September of 1977. But no, the data collected by the Apollo ALSEPs are still being used by scientists, providing discoveries even today. Even as recently as 2019, scientists used ALSEP data to understand the moon's tectonic activity, believing the moon continues to shrink over time. But what about the Artemis generation? What can radioisotope power do to support this future generation of explorers? Well, first we have to look at the technologies that we're going to have available for these purposes. The NASA RPS program works with the Department of Energy and continues to ensure the availability of the MMRTG. We're also designing a couple new systems to optimize use for power in deep space and to make more efficient use of that precious heat source, plutonium-238. A dynamic power system, or a DRPS, could achieve efficiencies on the order of 3 to 4 times that of the current state-of-the-art RTGs. A DRPS demonstration unit on the moon could provide use or could prove the use of dynamic power in space and make it an excellent candidate for future missions that otherwise might not be possible. The RPS program also continues to invest in the next generation thermoelectric system, improving on the SNAP-27 lessons learned from Apollo and the other system that were previously deployed. Well, regardless of the RPS type that might be employed, one needs to consider how one might use them on the surface of the moon. Of course, one would want to conduct science. There's already an Artemis 3 science definition team at work. Perhaps one would want to enable a process plant demonstration, for example, an in-situ resource utilization, there's a tongue-tire system, to extract water, oxygen from the lunar regolith. One might want to support the astronauts using a pressurized rover persistent power source, and perhaps one might power a human-tended robotic explorer. Nuclear power sources, like those of the SNAP-27s before, deployed by the Apollo crew, are bound to be advantageous for use by the Artemis astronauts as well. Power, and particular sustained power, for operation during the long lunar nights and within permanently shadowed regions will emerge as a critical lunar resource. Without power, there is no battery charging for tools, no life support, limited mobility, and long, long periods of darkness. Just remember, when traveling through the solar system, you will always need power. And Radioisotope Power has a long history of providing our NASA scientific missions the power to explore. Thank you.